Assalamualaikum to my examiner. My name is Zarifah Ashraf binti Zainul Abidin and I supervise under Prof. Professional Technologist Dr. Megat Ahmad Kamal Megat Hanafiah. Today I will present to you my final year project which titled Phosphoric Acid Treated Oil Palm Trunk Waste as a Biosorbent for the Removal of Malachite Grain from Aqueous Solutions. Chapter 1 Introduction. For background of study, complex aromatic compounds, called dyes, are used to color products in a range of industries, such as textile, paint, food, and pharmaceutical. According to Lim et al. 2022, the textile is responsible for the majority of existing dye effluents, with 54%, and followed by paper sector and print sector. Malachite green dye is exceedingly harmful to both human and aquatic lives, even at low quantities or at concentrations. There are few techniques that can be used to remove this dye, including flocculation, ion exchange, irradiation, and ozonation. But these methods are expensive. Adsorption is preferred method among them due to its ease of use, low cost, and have great efficiency. Adsorption is a desirable and practical method for eliminating colors from contaminated water samples. For adsorbent, we apply a low-cost alternative adsorbent where oil palm trunk waste is chosen, as these wastes are mostly composed of lignin, hemicellulose, and cellulose, which makes it desirable as adsorbent for removing a variety of contaminants, including dyes, heavy metals, and organic compounds. For problem statement, malachite green has been linked to various diseases including an increased risk of cancer, and it is extremely cytotoxic to mammalian cells and acts as a liver tumor promoter. These dyes are designed to be resistant to deterioration over time, which means they cannot be easily removed by the procedures that are often used to clean wastewater. According to Amar et al. 2022, nanofiltration, coagulation, electrochemical oxidation, biodegradation, and ozonation have been used by most researchers. These technologies remove color in industrial effluents, but they produce harmful byproducts and are expensive. Lastly, compared to other parts of oil palm, the utilization of all oil palm trunk as adsorbent has received a relatively small amount of attention. In significance of study, responsible parties need optimize the utilization of discard oil palm trunks rather than dumping them on the ground that can cause serious environmental issues. In connection with Sustainable Development Goal number 6, clean water and sanitation, the quality of wastewater needs to be treated in order to limit the discharge of hazardous chemicals and materials, reduce the amount of untreated wastewater, and significantly increase recycling and safe reuse around the world by the year 2030. There are three objectives for this experiment. First, to investigate the effectiveness of untreated and phosphoric acid-treated OPT as an adsorbent for the removal of malachite green dye from aqueous solution. Second, to characterize OPT by spectroscopic techniques which include FTIR, SAM-EDS, and PCs, and determine its physical and chemical properties. Third, to identify physicochemical parameters that might affect the effectiveness of malachite green removal from aqueous solutions. Chapter 2 Literature Review. For the literature review, the oil palm trunk is a lucrative crop in the tropics and a major industry in its own right. According to Lim and Lee 2022, oil palm trunk make up roughly 75% of solid waste and are readily accessible in plantation. Several studies have been conducted to investigate the feasibility of transforming this abundant and renewable biomass into high value end products with numerous potential applications. Malachite green is an organic compound that used in aquaculture as an antibacterial and in textile industry as dye. This dye is considered moderately hazardous and severely irritating by classification system used by European Union. According to Elbas et al. 2020, numerous chemical reagents such as sulfuric acid, phosphoric acid, hydrochloric acid, and sodium hydroxide are applied to modify the agricultural residual and wastes. Utilizing phosphoric acid is a significant part of an effective approach for enhancing the porosity and surface characteristics of the material. Next is Chapter 3 for methodology. For methodology, for preparation of untreated OPT, section of OPT was washed and dried at 60 degrees Celsius for 3 days. This dried section was manually cut into smaller size, ground, and sieved to obtain particle size of 0.5 to 1.0 nanometer, and this sample was stored in airtight plastic container and was ready to be used as untreated OPT. For preparation of phosphoric acid treated OPT without heating, 1 gram of OPT was mixed in 100 ml of phosphoric acid and stirred for 2 hours. The solution was filtered and washed with 100 ml of distilled water 10 times. The sample dried at 80 degrees Celsius for 2 hours and stored in plastic bottles. This untreated OPT and PaOPT was undergo quantitative and spectroscopy analysis, where FTIR, SMADS, UV spectrophotometer, and pH-ZPC was used, and then benchmark study that include absorption kinetic, absorption isotherm, pH, dosage, and desorption are determined to see efficacy of PaOPT as biosorbent in the removal of malachite green from aqueous solutions. Next is Chapter 4, Result and Discussion. Firstly, SEM analysis of OPT and PaOPT before and after absorption is identified by using 700 times magnification. SEM is crucial for detecting the surface accessibility of adsorbent for the absorption of contaminant compounds. From these 3 images, we can see the surface texture of OPT and PaOPT were completely different before and after absorption. SEM image reveals that OPT surface is porous and uneven. When modified, the adsorbent PaOPT becomes more porous due to cave-like, uneven, and rough surface. Newly created pores in PaOPT permit malachite green dye to be captured and absorbed over a large surface area. For EDS factorization, carbon, oxygen, and silica are the most abundant elements in untreated OPT, along with traces of magnesium and potassium. Small amount of silica was detected in this sample, which might aid in enhancing the adsorbent properties for removal of malachite green from aqueous solutions. After OPT being treated with phosphoric acid, only carbon and oxygen are present in the compound. Several elements such as magnesium and potassium have been eliminated. A new small peak of nitrogen was seen after malachite green and as adsorbed on PaOPT, which showing the dye was successfully adsorbed. Secondly is FTIR categorization. Based on this spectra, there is a connection between OH stretching frequency and the broad adsorption seen at the wave number 3335. The insignificant shift in the spectra of aliphatic methylene at 2899 and 2899.05 in PaOPT and PaOPT after adsorption was due to the CH stretching. In OPT, noticeable peak was shown at the wave number 1673 due to the stretching of conjugated carbonate in lignin. After OPT being treated with phosphoric acid, this peak disappeared, which suggests that carboxylic and ester linkage in hemicellulose lignin was broken. For PaOPT, the spectra show considerable drop in band intensity at wave number 1731 for CH deformation and 1504 for aromatic skeletal vibrations. This suggests the aromatic structure of lignin had been broken down. Medium peak for PaOPT after adsorption can be seen at wave number 1240 that represent a slight shift in CN stretching mode. Medium peak of NH family of amine can be in PaOPT and PaOPT after adsorption can be seen at the wave number 1594 and 1586 respectively. Thirdly is determination of pH-ZPC. pH-ZPC is the circumstance in which electric charge density on the surface of the adsorbent is 0. From this graph, pH-ZPC is the intersection of the curves between change in pH versus pH initial. pH-ZPC of PaOPT particles in aqueous solution is 4.5. At this phase, adsorbent surface becomes primarily positively charged and tends to reject cationic dye from being adsorbed. Fourthly is absorption kinetic. There are 2 types of kinetic models were used: pseudo first order PFO and pseudo second order PSO. In PFO, the number of occupied absorption sites is exactly proportional to the number of available absorption sites, while For PSO, hazardous compound absorption is determined by the number of reactive sites and the amount of ionized molecule on solution. From this table, correlation coefficient, which is R² of PFO, are low, while PSO has the greatest value from 0.70 to 0.99. Rate constant K2 reduced from 0.20 to 0.058 gram per milligram minute. At lower concentration of malachite green dyes, ions existent in the absorption medium could interact with binding sites. Hence, higher rate constant results. Analysis from chi-square revealed that PSO model was excellent at estimating the malachite green absorption. This shows that pseudo-second-order model can be used to predict the kinetic of malachite green absorption on PA/PT, as this model fits well with the absorption process. Fifth is the absorption isotherm. Absorption isotherm represents the phenomenon of retention or release of chemical from aqueous phase to solid phase. According to Langmuir, molecules can only adhere to biosorbent in monolayer during absorption, while Fredluck model depict multilayer absorption with distinct chemical interaction on non-uniform surface. Based on isotherm parameter, the Fredluck model has a lower value. R² for Langmuir and Fredluck was found to be greater than 0.9, with Langmuir 0.99 and Fredluck with 0.97. That means absorption of malachite green using PaOPT will be interpreted as mono and multi-layer absorption, but Langmuir model shows the maximum absorbent capacity of 217.23 mg per gram. Next parameter is focused on effect of pH. Absorption was favorably impacted by the rise in pH, and the amount of adsorbed dye increased in tandem with it. Graph shows at pH 3, malachite green exhibit a poor absorption capacity with 13.85 mg per liter, while at pH 7, malachite green exhibit a high absorption capacity with 46.025 mg per liter. At higher pH levels, there are more negatively charged sites, which threaten the electrostatic interaction between cationic malachite green molecules and the adsorbent, which contribute to increased amount of adsorb. 7 is effect of dosage. When adsorbent dosage increased from 0.02 to 0.1 grams, percentage of malachite green removal also increased from 76.04% to 92.04%. According to Krishnamurti et al. 2019, the possible for this tendency is that more active sites are available to bind dye from aqueous phase when dosage of adsorbent is increased. Next is Chapter 5, Conclusion and Recommendation. In conclusion, we can say that PaOPT shows promise as dye-removing adsorbents according to the result. The Langmuir isotherms give greatest match to the experimental data, thus its absorption capacity is 217.23 mg per gram was calculated. Pseudo-second-order model provide greatest fit experimental data on kinetics. Results of FTIR and scanning electron microscopy for PaOPT after absorption shows the malachite green was successfully removed from aqueous solutions, and when pH dosage and concentration were raised, it was found that absorption capacity also increased. For recommendation, because most of the published findings were obtained using batch and small-scale column absorption experiments, we need more research is needed to design more efficient adsorbents, analyze the absorption mechanism, and regenerate the spent adsorbents. Second, a mathematical model is needed to anticipate the influence of several variables such as BET and SRD analysis, agitation speed, and temperature. While response surface methodology is a step in the right direction, a lot more work has to be done to develop mathematical models that adequately account for all of relevant aspects. This is a few of reference that I use for this research. That's all from me. Thank you.